Alrighty, welcome to our last video for Unit 4 in 4.4 orthonormal basis and the Schmidt, essentially process factorization. In the last video, we essentially talked about how I can take a set of linearly independent columns, A1, A2, A3, and we can essentially transform them into a orthonormal basis, and through that we can use this orthonormal basis to solve problems much easier because of, again, the fact that orthonormal will not change the length. It keeps the calculation simple because of the way that the Q matrix multiplies. I'm going to kind of show that in a minute. And one of the last things that we talked about in the video was that, well, if we're starting with this matrix A and then we're transforming or creating this matrix from A, there has to be some kind of connection matrix that can transform or take Q back to A. Or better yet, some way that we can find that connecting matrix, which is what we're going to call R. And so we essentially take A and we can factor it into a orthonormal matrix, and then another matrix R, which is what we'll find out as upper triangular. And so it's very similar to when we factor the matrix into LU, similar to how we factor the matrix into CR, but the R that we found in Unit 1 is going to be very different from the R here. So try not to get too confused by those two notations used in the text, and then the same in the notes. Now, to help identify where this R is essentially coming from and why it's upper triangular, I wrote out essentially a reminder of how we find and determine our Q1, Q2, and Q3 in our example here, since we had a 3x3. And in this example, remember that Q1 was constructed by first finding an orthogonal vector and dividing by its magnitude, and then finding the error, the orthogonal vector that's perpendicular to this by definition, and dividing it by its magnitude, and then using from the third column in there, finding the orthogonal vector to that by subtracting off those error vectors. And each time we would, in terms of finding C, I would subtract off the other two. To find B, I would only subtract off A, and A we took as is as a starting point. And so because of that, I want you to think about the Schmidt process that we did in the previous video by looking at the three kind of rows here for the vectors as we were to walk through that process. So when we took in step 1, our initial vector A, in that case, was the 1, negative 1, 0, and we found our orthogonal vector, and then ultimately our orthonormal. All three of those vectors lie along the same line. Notice that B and C, lowercase b and c, uppercase b and c, and Q2, Q3 play no role in this very first setup and this very first vector. When we found our second one, AB, lowercase, capital AB, Q1, Q2, these all lie in the same plane. And again, once we determined B, we found B by only using A. We didn't use C. And so kind of step by step, as we go down the line of the columns, we increase the number of rows we need. And so that's why, essentially, when we're going to look at R and kind of define it in a minute, you're going to see for the very first column, there's only one piece because we didn't need the other rows. When I get to the second column for B, we're going to see the first two entries have non-zero components because we didn't need the third, versus for C, we need all three. And so that's going to form an upper triangular matrix. And again, we're going to see how that comes out of our work when we found Q in A. And again, he outlines this on page 182, and I think he outlines it very clearly. But I would love to essentially walk us through essentially how this comes to be. Remember that we were taking A1, A2, A3, really all the way out to AN, and we were essentially creating this matrix for Q. But to go back to A, so if I was to think about A1, A2, all the way out to AN, this has to be equal to Q, so Q1, Q2, all the way out to Qn. And I'm going to erase this. Just use my hand, so it's going to leave the board a little messy. But I have this. But to get back to A, B, and C, when I'm multiplying here, To get back to A, I would need to multiply Q1 by Q1 transpose A. If I do this multiplication, Q1 transpose is 1 because these are orthonormal, and I'm left with just A1. I don't want any of these others, and so this becomes zeros all the way down. And then when I look at the next one, I would be using Q1 transpose B, and then Q2 transpose B. But I don't need anything else because as I multiply this through, Q1 transpose gives me the B component, which is my A2. Q2 transpose and Q2 gives me 1, which leaves me with my B vector. And this, again, process would continue. I don't need anything underneath these entries. For the next one, I would have Q1 transpose C, and then Q2 transpose C, and then Q3 transpose C, and this would go all the way out to N. And so in our notations in terms of lowercase a, b, and c, if I wanted this again to be A, B, and C, this is the connecting matrix that would take us back to A once we've identified our orthonormal basis, Q, and our matrix Q. And so our goal is to ultimately try to figure out what this matrix is, and this again outlines exactly what that is. Notice that Q1 transpose A1, Q1 transpose all of this, is essentially looking at this factorization. R is an upper triangular, so if I'm just trying to figure out what R is equal to, notice how if I multiply on the left-hand side by Q transpose, because this is a square matrix in this case, and actually it doesn't matter because Q transpose is on the left, then this is the identity matrix. So to find R, I can take Q transpose times A, and that's what we're seeing here. If I multiply these two matrices together in this order, this is going to find my upper triangular matrix. And so I'd like to do that so you can kind of see where the numbers come out from. And again, the numbers are going to be kind of interesting. And he highlights the main diagonal, which is what I want to do as well. But again, I want to show you how those calculations happen. So first off, I need Q transpose. So I'm going to take Q. I'm going to write Q transpose underneath. Should have probably given myself a little more space. So I've got 1 root 2, negative 1 root 2, and 0. And then I've got, let's see, that's column 1, row 1. So column 2, so 1 root 6, 1 root 6, 1 root 3. I did this wrong, sorry. Negative 2 root 6. And then third column would become my third row, so 1 over root 3, 1 over root 3, 1 over root 3. That's Friday for this video, so happy Friday, TGIF. Perfect times for making mistakes. So I'm going to take this in a row by column. So if I multiply out here, so 1 over root 2 plus 1 over root 2 is 2 over root 2. There's my very first entry. And then notice if I go row, column, this is going to take the first entry and second entry and subtract them. So notice cancels. The third entry is always 0. So when I multiply these two, it creates 2 zeros underneath. And again, that's supposed to happen because we have an orthonormal matrix. So only the i's essentially will come out. So when I do the second one, this is going to take A and B and combine them. And so we're going to end up with a 0 for the C because we're not going to be using it. And so if I take row by column, so second column, this time this first and third entries will get doubled and subtracted. So doubled, but nothing here, so 2 over root 2. Same thing here. First entry is doubled, this entry is doubled, and this time it's going to be added. So 2 plus 4 is 6 over root 6. And then notice when I do this one, times 2 times negative 2, that's going to 0 out. So we've created the upper triangular matrix. Now again, I'm going to go row by column. Now notice this one is going to triple everything, where the second entry is going to be subtracted. So when I do this, I'm going to get 3 root 2 plus 3 over root 2, and then nothing, so 6 over root 2. When I take this one, it's going to be 3 over root 6 minus 3 over root 6, so that cancels, negative 6 over root 6. And then for our final, 3 over root 3, negative 3 over root 3, so that's 0, 3 over root 3. So if you're paying really close attention, all of these are irrational, with square roots in the denominator. So we want to rationalize these numbers. And again, if you're familiar in terms of unit circle, which you should be, 2 over root 2, really common with the pi over 4, the 45 degrees. When you're doing trig and trig reciprocals, 2 over root 2 is just root 2. So when you rationalize that, that creates just root 2. Anytime you see the number over its square root, when you rationalize, it is just the square root. And this is really interesting, just focusing on the diagonals, because these are the magnitudes of my vectors here. Again, notice first column, its magnitude is root 2. It's orthogonal was root 2. This one, second column is root 6. Third column was root 3. And so again, you see that along the main diagonal. If I rationalize this entry, just root 2. Now here when I'm rationalizing, this is going to be 6 root 2 over 2, or 3 root 2. If I make it a single square root, bring the 9 inside the root, it's square root of 18. Here this will result in just negative root 6. And then I have my upper triangular matrix here. And we now have our factorization. And we'll see in later units why this is important and how it connects and helps solve us problems. In the meantime, remember that when we were solving for x hat, for least squares and trying to find the answer that's closest to the point, recall that we were looking at ATA x hat is equal to ATB. And if we can transform A into QR, so if I can connect A to an orthonormal matrix, then I can plug this in. So I have QR transpose QR x hat is equal to QR transpose times B. When I transpose this, we'll swap the order. So Q transpose R transpose, sorry, R transpose first. I was getting ahead of myself. R transpose QR x hat. And then over here, R transpose Q transpose B. This is the identity matrix because we're talking about orthonormal matrices. So regardless if it's rectangular or square, that's the identity matrix. And I have R transpose R x hat, R transpose Q transpose B. I'm going to write this, I'll try to grab the eraser this time. I'm going to write this right here. So it's just one more single step. I'm going to write it a little bit cleaner. R transpose R x hat equals R transpose Q transpose B. If I invert R transpose, which is upper triangular, so I'll be able to, or transpose would make it lower triangular, these two would cancel each other out. In other words, this equation results in this format. I have an upper triangular matrix times x hat is equal to Q transpose B. And again, there's no inverse calculation here because we're talking about the transpose. And because this is upper triangular, remember the ease of upper triangular is that we can solve it through back substitution. In other words, this is solvable much faster than it was if we were to use another factorization. Thinking about LU and the computations needed, if you're somebody looking at the computational algebra aspect and using programming. Again, being a high school linear algebra course, not going to dive that deep in terms of the computational piece. But if you are, I would encourage you to check out the algorithm that he proposes in the textbook on page 183. But what we have is our least squares solution. X hat is equal to R inverse, so make sure I wrote that right, Q transpose B. So we can solve for this. Instead of solving AX is equal to B, which is impossible because we have a rectangular matrix, this we can solve by back substitution, which is really fast. And so again, he talks about the counting of the computations. And so that's why this is so helpful, is that this is much easier to solve than something that we couldn't even solve from the beginning, specifically if this is rectangular. So that is unit 4, that's chapter 4 in the text. That's chapter 4 for us, looking at orthogonal into projections, which ultimately builds up into orthonormal bases and creating an orthonormal matrix from a list of independent columns, and essentially looking at the Graham-Schmidt process.